So a ton of human research experiments take place on board the International Space Station because a lot happens to the human body when you're in microgravity. I'm joined now by one of the principal investigators for one such research study, Dr. Stephen Boyd, who's the PI for the TBone study. And you guys are looking at bones. You're looking at, kind of the deep insides of our bodies when you're up there. First off, give me a little general background. What happens to bones when you're up in microgravity?
Well, thanks, Dan. What we know that for sure where people are spending time in space, there's a lot of the lack of gravity, which is something that we experience every day on Earth, isn't existing anymore. And so with the lack of gravity, our bones actually adapt very quickly. So normally, as we get older, we'll lose about 1% of bone mass per year on Earth, but when we're in space, actually, we can lose up to 1 to 1.5% per month.
So it's kind of like aging in fast motion almost.
Exactly. It's a really accelerated aging process for your bones. And so that can really affect, the most important thing is it'll affect your bone strength possibly. So what we're interested in is what happens in the space environment in terms of the bones, both in terms of how much bone loss that occurs and how that might influence the bone strength.
Okay, and you guys are going to be testing out a new technique for this research study. Why don't you tell me a little bit about what you guys are doing that's new to help track this bone loss in the astronauts?
Well, the typical way that people measure bones is they look at bone density, and that's a standard tool we use on Earth all the time for measuring how well people's bones are adapted to their function. The problem with bone density is it's really a measure of how much bone we have. What we're using is a new tool that can measure at very high resolution the three-dimensional bone architecture. We do this at the wrist and ankle of people, but we can measure at a resolution of about 60 micrometers, which, if you compare it to human hair, which is about 100 micrometers,
oh wow,
it's very fine detail. So as opposed to looking at density, what we're interested in is looking at the underlying structure. Density is an important measure, and it's typically of interest because it can relate to how strong somebody's bones are. But fundamentally, what we really want to know is the strength of the bones, not particularly their density. And so by looking at this detailed microarchitecture, this detailed structure, we get a much better idea of what's going on in terms of adaptation to the loads or lack thereof in space.
So really just kind of getting the whole picture. So I know one of the other things you guys are looking for is actually the susceptibility that individuals might have to bone loss. Is that true?
That's right. So if we can look at the long-term effects of this bone loss in space with the astronauts, we will be able to track very precisely how that architecture changes over time. And so when we get a better understanding of how that architecture relates to the bone strength, then we can use that information so that when we bring a new person into a study or an investigation, we can already see where they are relative to the other data that we've already collected.
So what is this study going to mean for future space flyers? What are you guys hoping to learn from this that's going to, make the job easier, make the job better for the astronauts of tomorrow?
Well, we're really wanting to shift away or add to, I guess, our measures of bone density to understand the long-term consequences. So what's really interesting for us actually is not only what happens to the bones during space, but what happens during the recovery period. So typically the way we measure recovery right now for bones is we look at bone density, and typically after a year or so people get back to close to normal levels after being in space. But what we know is that the underlying microarchitecture, the structure underneath, may not be the same as it was before they left Earth. And so that kind of information will not only be important for understanding long-term space flight for our astronauts, but it will also be important for understanding the long-term implications of bone architectural changes in people on Earth.
Okay. So, and final question. So we talked a little bit about the beginning how being in space is kind of like aging. Everybody down here on Earth is aging, obviously. Are there going to be any benefits for those of us down here that aren't going to space from research like this?
Yeah, absolutely. I mean, as you said at the outset of this discussion, that this is really a model in space of accelerated aging. So what we can learn in 6 months of space flight would take us a decade on Earth. So this really accelerates the whole process of learning how microarchitecture relates to bone strength in the end. So we're really interested in these outcomes.
No, very, very cool stuff. Again, Dr. Stephen Boyd, the principal investigator of TBone, one of the new bone studies taking place right now on board the International Space Station. Doctor, thanks so much for joining me today. Really appreciate your time.
Thanks, Dan.